Homework 10, question 1. The question 1 is asking us to find the definition and the simple property of the several examples of stochastic processes. The first one is the Poisson processes. After reviewing the lecture provided by professor, we have already know that the probability of the Poisson processes is mean that the number of the point in the interval of the t1 and t2 is k, and this is the probability mass function of that is equal to e to the power of minus lambda t and multiplied by this stuff. And it has several properties. The first one, if if in the interval t1, t2, and t3 and t4 are non-overlapping, then the random variable n t1, t2, and n t3, t4 are independent. At the time moment t, there is no more than one Poisson point. X of t is equal to n0 t. And for that, the first order probability mass function is equal to this one. And the mean of the Poisson process is equal to lambda t. And the autocorrelation is equal to lambda square multiplied t1, t2. Add with lambda, the minimum of t1, t2. And the autocovariance is equal to lambda square multiplied t1, t2. This function, and after calculation is equal to lambda to the multiplied by the minimum of t1, t2. And for the second one is asking about the Poisson increment process. Yt is the Poisson increment process equal to x of t plus epsilon minus x of t divided by epsilon. X of t is a Poisson process. And for this part, we have the probability mass function is equal to e to the power of lambda epsilon multiplied lambda epsilon the power of n divided by the factorial of n. And so that the mean of the Poisson increment process equal to lambda. And correlationship is equal to this part. And the autocovariance is equal to this part. And for the third one, the Poisson impulse processes. We have the impulse processes is mean that in this point, it has the impulse of 1, just like this graph. And for this process, it has no probability mass function, and it has mean of the Poisson impulse process is equal to lambda. So correlation is equal to lambda squared plus lambda multiplied by delta t1 minus t2. And covariance is equal to this part. And for the fourth one, the semi-random telegraph signal, the mass probability function is equal to e to the power of minus lambda t multiplied by lambda t to the power of k divided by k factorial of k. And xt is this kind of function. And the first order of the probability mass function is equal to when x of t is equal to 1. The probability of this condition is equal to e to the minus power of t minus lambda t multiply e lambda epsilon e lambda t plus e minus lambda t divided by 2. And for minus 1, this part is changed to the minus 1 minus. And the mean of this process is equal to e to the power of minus 2 lambda t. Correlation is equal to e to the power of minus 2 lambda we multiply by the absolution of the T1 minus T2 covariance is equal to this kind of function. And for the fifth, the random telephone signal is equal to the probability of this kind of process is equal to 1/2, and the mean of this part is equal to 0. Correlationship is equal to this kind of function. Covariance is equal to this function. And for the random walk process, the probability of x of t equal to x of t, f of nt is equal to rs is this kind of function on this condition, and the mean of that is equal to 0. Correlationship is equal to this kind of correlation is equal to this kind of function with we got is minimal of and multiplied by I square, and the covariance is equal to the minimum of and multiply I square. And for the seventh, the Wenhan process, we got the probability the density function is equal to 1 over the root of 2 pi alpha t multiplied by e to the power of minus w squared over 2 alpha t, and the unconditional probability density function, which follows normal distribution with mean equal to 0 and variance equal to t at a fixed time t. The density function of omega t x is equal to 1 over the root of 2 pi t multiply e to the x squared over 2t, and the mean of this part is equal to 0.